Yeah, so this talk is really nicely placed in the schedule. I'm going to be tying together the two themes from the first session, the causal models and the contextuality by default, or more generally, extensions of contextuality to inconsistently connected systems. Causality has always been fundamental to contextuality. For example, the factorizable models that Bell considered in his original theorem embody a theory of causality that's represented in this graph here, where Alice's outcome depends only on her setting and the hidden state, and so likewise for Bob. The factorizability condition can be decomposed into two different prohibitions on additional additional causal effects within this graph, namely parameter dependence, meaning connections from one observer's settings to the other observer's outcome, and outcome dependence, meaning direct causal influences between the outcomes. The same situation applies in Coach and Specker models. So non-contextual models are defined such that the outcomes depend only on the hidden state and not on what other measurements are made. And according to the Fine-Abramsky-Brandenburger theorem, this is equivalent to a very similar factorizability condition. Now, these prohibitions on this restriction of the causal connections among the variables are essential to the theorems in that without them, they don't hold. It's very easy to show that if you add parameter dependence to this model, then the model can produce any pattern of data whatsoever. And outcome dependence has very nearly the same property. So it's useful to think about, well, what is the basis for restrictions on causal relationships among variables? And there are basically two arguments that are often given in the literature. One is an a priori theoretical one based on relativity and space-like separation between the observers. And another one is a data-driven one based on the principle of no fine-tuning that Pearl and Cavalcante talked about earlier today, where you use conditional independence relationships in the data to infer restrictions on the causal connections in the graph. So for example, if Bob's outcome is independent of Alice's setting, you infer that there should be no causal connection from Alice to Bob. Now, importantly, both of these approaches are all or none, and in the sense that they outright prohibit certain causal connections. And consequently, they give the traditional notion of contextuality that's restricted to consistently connected systems where the marginal distributions of each outcome are the same across contexts. Now, there's been a lot of important work, most prominently in the CBD tradition, of extending contextuality to situations where consistent connectedness is violated. So CBD is not a causal theory, it's expressed in the language of probability, but it captures this idea of, well, as Edibar and Victor described earlier today, you can define non-contextuality based on the degree to which you can impose a coupling, which is a form of joint distribution across all contexts that minimizes the difference between variables representing the same observable in different contexts. And this kind of extension is really useful because it allows the contextuality to be expanded to physical systems that involve direct influence and experimental settings where, just due to the sampling statistics of the data, marginal invariance is violated. So my work has been aimed at giving a causal models interpretation to CBD. So I've been following the same causal models approach that was developed by Cavalcante that we saw earlier today, but instead of limiting which causal connections can be present in a model, my approach bounds how strong those connections can be. So I define a notion of direct influence, which is a quantity of the strength of effect of context on any one of the outcome variables, shown here as these F1 through F4. As for any two contexts in which some variable is measured, we can look at the probability of all hidden states for which a shift of the context would change the outcome of the observable in question. A particular kind of direct influence of interest is what I call hidden influence, which are influences, direct influences that go in opposite directions for different values of the hidden state in a way that leads them to cancel out when we marginalize over the hidden state. So for any value V of our outcome and any two contexts C and C prime where the measurement is made, switching between C and C prime can lead the outcome to change from V to something else for some lambdas and vice versa for other lambdas. And those both happen with positive probability, such that when we average over lambda, the difference in the empirical distribution is less than the strength of the direct influence. And this is summarized in this proposition that says the direct influence is minimized, it equals the difference in empirical distributions precisely when there's no hidden influence. So hidden influence captures this idea of direct influences that cannot be observed. And using that, I proposed an extension of contextuality that I called model-based contextuality, by which a system is M-contextual if modeling it requires hidden influences. And then I proved that M-contextuality is equivalent to CBD contextuality. So this puts CBD on causal model's footing and gives it the same kind of no-go interpretation that Bell's original theorem has. It also formalizes several proposals made by other people in this group. Cervantes and Javarov wrote this as a no conspiracy principle that says that all known to us examples of direct hidden influences are artificially constructed. Javarov wrote that direct influences are not revealed in distributional differences only under special precariously set circumstances. Cavalcanti wrote similarly of what he called a generalized no fine-tuning principle, whereby causal connection should not be stronger than needed to explain observed distributional differences. And so this notion of hidden influences formalizes these proposals and shows that CBD contextuality embodies that principle. However, these previous results are limited to what I call canonical causal models. That's the asterisk here. The canonical models are the structure that I've shown you previously. And what I want to do is here is extend these results or see how they extend to other graphical structures. So once again, this canonical structure that I've previously studied looks like this. So you have a variable for the context, a hidden variable, and then outcome variables for each one of the measurements. And then causal connections as shown here. This is what I call a Cauchy-Specker representation. You can also do the same thing with the Bell representation. The Bell representation is what Cavalcanti and Pearl use. So those are the graphs you saw earlier today. The two graphs are equivalent when a scenario is compatible with the Bell representation. The Bell representation simply takes the context and splits it into a set of variables representing the settings for all the different observers. And so in either case, we can think about effects of, in the Cauchy-Specker model, effects of context on the outcome. And in the Bell model, we can talk about these parameter dependencies, these signaling arrows, the gray arrows in both cases. If we prohibit hidden influences in either model, we get a definition of non-contextuality that's equivalent to CBDs and also that agrees with Cauchy-Specker contextuality when we restrict to consistently connected systems. But there's a whole zoo of other graphical structures we might want to consider. Things like causal connections directly between the observables, intervening hidden variables, and so on. And it's possible that defining contextuality with respect to these other structures will lead to different criteria, and thereby different extensions of traditional contextuality from the extension that we get from CBD. So to give a motivating example of how this could happen, this system is a two-cycle in the sense that Edibar described earlier today. We have two variables, x and y, that are jointly measured in context 1 and 2, C1 and C2. KS contextuality doesn't apply in this situation because the joint distribution differs between contexts. So this is neither KS contextual nor KS non-contextual, but according to CBD, it is contextual. And by my theorem, that means that it cannot be modeled under this kind of graph structure without hidden influence. In fact, the best you can do doesn't even use the full structure. I'll show you a model based on this simplified model, simplified graph, whereby x is determined purely randomly as a function of lambda, and y depends on lambda in a way that differs across the two contexts. And this is where, in this model, the hidden influence lies. So between C1 and C2, y changes in opposite directions depending on the value of lambda. And when we marginalize over lambda, we can't see that influence at all. The distribution of y is the same in the two contexts. So hidden influence, and this is, from the model-based perspective, this is why the system is contextual. However, if we consider a different graphical structure, a different causal structure, where y depends on x instead of lambda, we can get a non-contextual model, a model that has no hidden influences. So this model is essentially the same as the one above. We've just replaced y's dependence on c and lambda with a dependence on c and x. But c and x are both observable. Y is a deterministic function of two observable functions. There's nothing hidden here. There are no hidden influences. And so by the same reasoning, we should say that under this graphical structure, the very same phenomenon should be classified as non-contextual. So it depends on what sort of graphical model we're considering. All right, so based on all these ideas, I want to propose a notion of graph-based contextuality, whereby a behavior is non-contextual, or sorry, a behavior is G contextual if modeling P on G requires hidden influence. So for example, we can consider the canonical graph structure that I previously analyzed, which I'm now going to call GPD for parameter dependence. So this is the model that has these signaling arrows. And talk about contextuality with respect to that graph, right? So contextuality, G-contextuality with respect to this graph is the same as M-contextuality as I previously defined. And therefore, by my previous theorem, it's equivalent to CBD contextuality. And for consistent with connected systems, it's equivalent to KS contextuality. We can also talk about other graphs or families of graphs. So I can talk about the family of graphs with outcome dependence with this somewhat distracting acronym, where in this case, we have to consider two different graphs because the direction of the causal influence could go one way or the other. But I can ask again whether any behavior can be modeled under one of these graphs without hidden influence and define G contextuality with respect to this family of graphs. Okay, so the questions that this all leads to, first of all, do different choices of graph lead to different variants of contextuality? In other words, this consideration of different causal paths change what we're going to classify as a conspiracy, as a hidden influence, and therefore what we should consider as a contextual system. Or alternatively, do most reasonable representations of causality lead to the same notion of contextuality, namely the one given by CBD? Next question, to the extent that we do get different versions of contextuality, which of these are useful or sensible as opposed to being degenerate in some way? The particular requirement I'll focus on here, which turns out to get us pretty far, is that the definition of contextuality restrict to KS contextuality on consistently connected systems. In other words, we want a proper extension of KS contextuality, not some wholly new concept. And to preview my main conclusions, it turns out that using different graph structures does indeed yield different alternative extensions for contextuality. So we're going to get different variants of contextuality beyond the one that CBD has offered. But they're almost all degenerate or unreasonable. In particular, they fail to agree with KS contextuality on consistently connected systems. And consequently, it seems that the canonical graph structure, this parameter dependence graph, and also CBD contextuality, they appear to be the only well-behaved notions of extended contextuality within this space. And so this gives a new sort of justification for why CBD contextuality needs to be defined in the way that it is. Okay, so now that I've sort of laid everything out, in the second half of my talk, I'll go through technical details. I'll start by talking about some of the details of how you have to define hidden influence and arbitrary causal models. There's some additional complications that arise. Once we do that, then we can lay out the space of all possible graphs that need to be considered. And then I'll talk about properties of G-contextuality for some prominent graphs within this space. And then wrap up. Okay. So arbitrary causal models. Here we have gray nodes representing observable variables, so either the settings of an observer or the measurement outcomes that they measure, and then white nodes representing unobservable hidden variables. And for each one of our observed variables, we want to define a notion of hidden influence based on that variable and how it depends on its immediate parents. What we do is we take the parents and we split them, we partition them into the observed and the unobserved. And the question we want to ask, as before, is whether the observed variables have an influence on our outcome variable x that becomes hidden when we marginalize over the hidden parents. Now, in order for this to work, x has to be a deterministic function of its parents. And we can do this if x is probabilistic by simply introducing the sample space as an additional hidden variable. So for example, if x is some Gaussian variant with known mean and variance, then we can just introduce a z-score random hidden variable that captures the randomness sample space, and now x is just an arithmetic function of its parents. Once we do that, then we can define hidden influence essentially as we did before, just combining all of the hidden variables, hidden parents of x, and combining all of the observable parents of x. So for any two values, c and c prime, that are configurations of all the observed parents of x, we can ask, what happens when we shift between c and c prime? Are there values lambda that are configurations of all the hidden parents for which the outcome x shifts from, say, v to something else, and then other values of lambda where it shifts in the opposite direction? Once again, if that's the case, this is what we call hidden influence, and it's influence such that once we marginalize over the hidden parents, the observable distributions differ by less than the model actually requires, or than the model produces. The direct influences are stronger than the observable. Okay, there's one other complication, and it's what I call a problem of hidden mediating variables. It produces the sort of annoying result that given any model M, I can always remove all hidden influences by putting intervening hidden variables in. So for example, if I have X depending on one observable parent and one unobservable parent, I can create a new model where I just stick phi in between. Phi is nothing but the tuple of A and lambda, and X has the same dependence, it just carries through. And if you look at this graph, there's no hidden influence here, either on phi or on X. Well, this is clearly cheating. This sort of ruins the idea of hidden influence. We obviously just want to ignore mediating variables like this. So I define hidden influence in a way that skips over any hidden mediating variables. So the only hidden variables we consider are ones that are primitive, that have no parents. And this is sort of an algorithm describing how that works. But with that in mind, we can now define all possible graphs that we need to consider. All right? So first of all, I'm going to restrict to Bell representations. Again, this is the style of graph where the context is represented. It's decomposed into settings for different observers. This is the same setup that Pearl and Cavalcanti used. So it's the graph that you're used to seeing from earlier today. Note that there's no loss of generality. So for any Coach-Inspector contextuality scenario, I can just assign a separate observer to every observable and put it in this kind of Bell representation. So I don't lose anything by doing this. Under the Bell representation, there are three types of nodes, or sorry, my connectionist language from psychology, three types of variables. So for every observer K, we have their settings, context, we have their outcome variable F sub K, and then we have hidden variables in M. And the hidden variables can be collapsed to a single variable using the skipping over mediating variables that I described on the previous slide, and then taking all the remaining variables, which necessarily have no parents, and just combining them into a single composite variable. So these are the variables in the model, all possible variables that we have to consider. Finally, I exclude superdeterminism. This is something I'm still working on, but for now, I assume that the contexts have no parents. They're freely determined by the observers. And then based on all these assumptions, all these arguments, we can list out the possible connections that can be present in our model. So we have local settings, the effect of each observer's setting on their outcome. We have source dependence, the effect of the hidden variable. We have parameter dependence, the effect of settings on other observers' variables. And we have outcome dependence, direct connections among the outcomes. So this is sort of a master map of all the graphs that we have to consider. And now let's talk about possible graph structures that are sort of subsets of this map. Okay? So first of all, we've got the Bell locality model, the one that has no non-local connections, no parameter dependence or outcome dependence. So this is essentially Bell's original model. We have the model with parameter dependence. This is what I previously called canonical models that I analyzed in my previous work that I presented at this meeting 2 years ago. We have a model that has just outcome dependence, and we have a family of models, and then we have a family of models that include both parameter and outcome dependence. And then there's a whole array of other models that we can define by allowing only a particular subset of connections of each type, possibly motivated by considerations of the physical system under study. For example, if you think about a Leggett-Gard type of scenario that has a temporal order into the measurements, we might want to allow dependencies only in the forward direction. So domain-specific models that we might want to consider as well. Okay, so what form of G-contextuality do each of these models give us? Well, for the Bell locality model, there are no non-local influences, there's no hidden influences to consider, and so by Bell's theorem, we know that this is just equivalent to KS contextuality. The parameter dependence model is the one that I previously analyzed, defined as M contextuality, and proved as equivalent to CBD contextuality. But these other models that involve outcome dependence are previously unexplored, and it's these two in particular that I want to focus on now. So I'll talk about first the OD-PD model and the full model, and then I'll talk about the model with just outcome dependence. All right, so the model with both parameter and outcome dependence. First of all, you can prove that G contextuality with respect to this model family is strictly stronger than CBD contextuality. It's stronger because the parameter dependence model that's equivalent to CBD contextuality is, of course, a subgraph of any graph with also outcome dependence. The strict part of this proposition, you'll see from the example on the next slide, but there are cases that are CBD contextual, but they're non-contextual with respect to this. Moreover, even though G contextuality with respect to this graph is stronger, it's not empty. There are situations that are contextual with respect to this graph. Here's an example that I basically just elaborated from an example of Jabarov and Chiala, where Alice has 3 settings, Bob has a ternary variable, and the rest of the scenario is degenerate basically, and there's no non-contextual model on this graph structure, no model without hidden influences. So this is a case of a system that is G-contextual with respect to this structure. So we have now a new form of contextuality, G-contextuality defined with respect to this graph family. It's different from CBD, but unfortunately it has one, what I consider a pretty serious problem. It doesn't agree with KS contextuality. It's in fact too strong. In fact, we can produce a non-contextual model of the PR box, which is pretty bad, right? The model works like this. I don't even need the full graph, just the black arrows here. A depends on lambda purely randomly, and then B depends on the settings and on the other outcomes, so little a, little b, and big B, and big A. As shown in this table here. And as in the example I showed you at the beginning, B depends only on observable variables. So there are no hidden influences. There's no effective lambda whatsoever on B. Okay, so this is a non-contextual model, and it shows that the PR box is G non-contextual with respect to this complete graph. Okay, so that's a big problem with this graph family. Let's move on to the model with just outcome dependence. It turns out this model is also too flexible. It also, in fact, allows for a non-contextual model of the PR box. In this case, Alice's outcome has to depend on both her setting and the hidden variable, and Bob's outcome also depends on the hidden variable. But if you look at the table on the right, those dependencies are fully observable. If you marginalize over lambda, the direct influences show up in the marginal distribution, so there's no hidden influence there. Now, you might look at the table on the left and say, wait, there are hidden influences on A, right? Alice's outcome depends on her settings in a way that cancels out when we marginalize over lambda. And so I would call that local hidden influence. And we could consider, what if we expand the definition to prohibit local hidden influence as well? Well, first of all, let me point out that this is conceptually problematic because we usually think of different settings as corresponding to different observables, like different Pauli matrices or something. And to really put a point on it, if we just took our apparatus and turned it upside down, or just arbitrarily relabeled how we record our data, that would produce hidden influence in a way that was, pretty empty. But despite those conceptual problems, those are really theoretical problems. They're not actually directly observable. And from a strict operational standpoint, we might want to say that it makes sense to prohibit local hidden influence as well. So we could add that to the definition of G-contextuality, just to be thorough. And but what turns out to happen is that this makes the graph, the outcome dependence graph family, too restrictive. Now we have cases that are G-contextual but KS non-contextual. So here's an example of that. This is a non-contextual system where A1 and B1 are perfectly correlated and they're anti-correlated with A2 and B2. That's what the KS non-contextual model looks like. It's just a joint distribution over those two configurations. But it is contextual with respect to the outcome dependence graph. You might also ask what happens if we prohibit local hidden influences in the full graph, and that leaves the PR box still non-contextual. So I've sort of bounced back and forth and given you a number of different results here. But the theme here across all of these is that everything that we're considering is either too restrictive or too flexible. Nothing agrees with Cauchy-Specker contextuality, except for the original graph structure, the parameter dependence graph structure, the one that's corresponding to CBD. One last thing I tried out was, what if we combine G-contextuality with the no fine-tuning principle? So rather than considering different graphs a priori and saying what kind of G-contextuality do they provide, let's set the principle of no fine-tuning and the pattern of independence relationships in the data determine which graph structures are allowable, and then use no hidden influence to ask whether those graphs admit a G non-contextual model. So one nice feature of what I'll call G-contextuality under no fine-tuning is that it meets my primary criterion of agreeing with Cauchy-Specker contextuality on consistently connected systems. And this fact follows directly from Perl and Cavalcani's theorem that Jason presented this morning. However, in general systems that don't obey any exact independence relationships, then the model that applies that you get out of no fine-tuning is just the full model with all outcome parameter dependencies possible. And for my final theorem here, this graph is just far too flexible. If your observables are binary, then you can model absolutely anything under this graph without hidden influences, without even any local hidden influences. And the proof of this is basically an induction on the observers. You just add one observers one at a time, based on a theorem of Javarov and Fiala having to do with couplings of binary random variables. And so as a corollary, this G non-contextuality under no fine-tuning has no non-contextual systems outside of ones that obey exact conditional independences if we're looking at binary observables. Okay, so conclusions. I've argued that Bell and Cauchy-Spector contextuality are predicated on prohibitions of direct causal influences. And if we generalize this, if we relax this to prohibitions against hidden influences, then we get extensions to contextuality that go beyond consistently connected systems and yet retain the no-go character of the Bell and Cauchy-Spector theorems. So we can talk about contextual systems as being those systems that cannot be modeled by a certain class of theories. What we see here is that different causal graph structures lead to different variants of contextuality under this approach, but only one of them agrees with Cauchy-Spector contextuality, and it's the one that I previously analyzed, defined as M contextuality and is equivalent to CBD contextuality. And so the bottom line, and I'm kind of surprised by this conclusion, but it seems that CBD contextuality is unique within this space. It's a unique extension that admits this kind of this no-go interpretation that's consistent with Cauchy-Spector contextuality. The only caveat being that this no conspiracy principle that's been used to justify CBD contextuality has to be limited to parameter dependence, so signaling rather than outcome dependence, direct dependencies among the outcomes. And that's it. Thanks very much.
So maybe I have a very basic question, if I may ask.
Yeah, please.
Yes, so thanks for the nice talk. I was a bit, so yes, as I said, it's something very basic, but just to better understand your model. So if I had no knowledge of quantum mechanics, now you will give me some of these graphs, and then if my data somehow what do you say, like violates the condition imposed at this graph, I will just say, okay, this graph maybe is not the correct representation. Now, for instance, you mentioned when you have the dependence of the outcome from the settings of the other party, you can simulate a PR box, right?
Yeah.
But I will say, if I have this graph, I imagine there is some sort of communication. So it's not that strange that that you can simulate also a PR box. So if you can communicate, you can also do the PR box. So I was trying to understand what is the connection between your initial assumption on the graph and maybe the physical scenario that you have. So why do you speak about contextuality rather than say, okay, maybe this causal structure somehow fails because of,
right.
I don't know, because of the physical situation, let's say.
Yeah. So my take on the the arguments behind traditional contextuality is precisely what you're saying, is that by considerations of the physical setting, we make a priori assumptions about what is the proper causal graph, right? So this is the space-like separation argument that goes back to Bell. And if such considerations are available, then fine, you can just use the Bell locality model, and that would be the appropriate model, and traditional contextuality applies. But that all breaks down as soon as you have systems that have disturbance, right? So if there's disturbance, yes, then necessarily, space-like separation doesn't apply, and you cannot rule out a priori causal connections, right? So causal connections are present. And this is the same thing that Edibar and colleagues have been doing all along, to say, well, if once direct influence is present, what do we do, right? We have to limit it somehow. If we want contextuality as a concept to apply at all, we need some sort of way of limiting it. And if you don't have, right. And so anyway, my approach here that turns out to be equivalent to CBD is to say, well, we're not going to outright prohibit causal connections, but we're going to prohibit causal connections that have this feature of hidden influence, that once you marginalize over the hidden state, they go away or they lessen.
Okay, but maybe just to explain, to follow up on this. So except for the Bell scenario, which is clear, you have this space-like separation, locality, and so on.
Right.
How do you decide which is the correct graph, or how do you connect the graph with your?
Well, yeah, I mean, and so that's been my approach here, is to say, well, if you don't have any domain-specific knowledge for what the correct graph is, then there is no basis, and we need to, and so that's why I did this exhaustive exploration of the different graphs. Which graphs give us gives us useful definitions of contextuality. So the conclusion here that only this parameter dependence graph, this is the only one that gives a reasonable definition of contextuality. We're left with this open question of, well, why? And why is that special? And why should it be the one that we consider? It's interesting that it's the one that CBD used. Well, it's not so coincidental, because of course CBD was developed and already shown to be an interesting, useful extension of contextuality. But the surprising thing is that it's the only useful one. And that's not because of domain-specific considerations or any a priori arguments about why one graph is more appropriate than another. I don't have any such arguments for why the parameter dependence graph is the one we should consider. It just happens to be the only one that works.
Okay. Okay, I see. Thanks for the explanation.